Welcome to Chapter 12, Chemical Kinetics. In this chapter, we are going to look at an area of chemistry that we have not looked at really at all up to this point. Most of what we've covered in this class so far is at least related to stuff that we had talked about before. Um, the intermolecular forces that's related to whether molecules are polar or not, which we had discussed in Chem 1, and solutions was related to that as well. Everything was kind of connected. This is kind of a whole new topic here. Chemical kinetics is really a study of the speed at which reactions occur. It's how slowly or how quickly reactions occur and why they occur very slowly or very quickly. We're going to get into reaction mechanisms a bit at the end of this chapter, which is the study of the actual how do reactions occur step by step. Because up to this point, we've kind of just pretended that you have reactants and you have products and one just goes to the other. But in reality, the vast majority of chemical reactions are actually multi-step processes where you have two things maybe coming together to form some new molecule, but then that thing goes off and reacts with something else, and there's multiple steps before you get to the end of the process. So we're going to be taking a look at that as well. But to start off here, just to introduce you to the idea of chemical kinetics, let's talk about the reaction rate. So the reaction rate is the speed at which a chemical reaction occurs. How fast or how slow, in some cases, the reaction is occurring. So this rate is just like any other rate that you would come across. So your speed in your car when you're driving down the highway is also a rate. It is the change in some quantity over a certain period of time. So the speed of your car, if you're going down the turnpike, is probably 75 miles per hour. So it's the change in your position, essentially. That's the 75 miles divided by a certain period of time in an hour. You go 75 miles in an hour. That's a rate. Chemical reactions do the same thing. Except instead of miles per hour, we are going to use a change in a concentration over a change in time. And usually the change in time is not going to be hours. It is sometimes. For some of the slower reactions, you might have the change in the concentration per hour. But for most of the ones we're going to see, it's going to be per second instead, because we don't want to sit around waiting for chemical reactions to occur for hours. We'd much rather look at faster ones. So the rate, if we're going to mathematically define it, would look something like this. So the rate is equal to, in the case of this particular reaction here, we have hydrogen gas and iodine gas coming together to make hydroiodic acid, HI. And so the rate could be described as the change in the concentration of H2 divided by the change in time. So how much does the concentration change in a certain period of time? Now notice the little negative sign here. The reason we have a negative sign is not because that's there. That's just a bullet point. It's because the hydrogen is a reactant. Because it's a reactant, it's disappearing. We're losing it. Its concentration is decreasing. So because it is decreasing, we still want our rate to be positive. We always want our rate to be positive. And so because this change in H2 is negative, we need a negative out here at the beginning to make the overall rate positive. If we were to define the rate in terms of the products, we wouldn't put that in there, which we'll see in just a minute. If we want to expand this out just a little bit, it would look like this. So this is the same thing, just showing the final and initial. for each of them, because remember, anytime we have a delta something, it is always final minus initial. So if we were going to expand this out, it would be the concentration of H2 at the second time minus the concentration at the first time, divided by the time 2 minus time 1. And usually when we do this, time 1 is just 0. So it's really just however many seconds here. But there are a few special cases where you might have, maybe if you're measuring the time at different points along a reaction, you might be measuring it at 0 and 10 and 20 and 30, which I think we'll actually see an example of this in just a second. And so the delta T would be 10 each time. Okay, so at the molecular level, what's happening here is that you're starting with reactant molecules, and as time goes by, you're converting those into products. Again, up to this point, we've always really just assumed that you had reactants, and then the reaction occurs, and you have products. But in reality, this process takes time. It's not an instantaneous thing. Even technically speaking, for really fast reactions, it still takes some amount of time, although you can get ludicrously fast reactions where you literally can't even see the reaction finish because the time it takes you to blink, the reaction is just done. But that's fairly rare. Most reactions do take at least a few seconds to occur. And some of them take a very long time. So as you can see in the two examples here, this reaction on the left, it is pretty much done after, looks like about 30 seconds, and it is completely done by 45 seconds. The only thing you have left is product at that point. But then there's another reaction that has the same overall chemical process happening here. You have two things coming together to make a third thing. And this, after 45 seconds, is still maybe halfway done. So it's much slower. Even though overall it looks pretty much the same in terms of the reaction that's occurring, for reasons that we'll get into later, it is much, much slower than the first reaction. Alright, so continuing here, talking about the rate. If we're trying to get the rate from raw data, so this is what raw data would look like if you were just measuring the concentration of something at different points of time as the reaction occurs. What you would do is to find delta T, kind of similar to what we said earlier. We're taking a measurement every 10 seconds. Delta T would just be one time minus the previous time, so it's just 10 seconds each time for that. Delta H would just be one concentration minus the previous one. So for this delta H, it's this one minus that one, but then for the next one, now this is the concentration that is subtracted. So it'd be this one minus that, and then this one minus that. And so you just, as you go along, you subtract one concentration from the next. And so then each of these you would divide by the delta T's. So you're just dividing this number by 10 in this particular case. So one thing that we'd like to notice here is that when we calculate the rate for this reaction, and we look at the rate starting at the beginning as the reaction proceeds, hopefully you can see here that the rate is gradually getting slower and slower. This is going to be the case for every single reaction that we come across. Now, there are some reactions that are exceptions to this because, there's exceptions to everything in science. But all of the reactions that we are going to look at, as the reaction proceeds, it is going to get slower. And by the way, those exceptions, they have really weird stuff going on. They're not normal chemical reactions. The vast, vast, vast majority of chemical reactions. As they proceed, they go slower. So in this case here, we have H2 that is reacting and forming HI. This is one of the products. And the reason why the reaction goes slower is because as time goes by, the amount of reactant that you have is decreasing. We have less and less reactants for the reaction to occur with, which means that the well, let's think about it this way. For the reaction to occur, you have to have an H2 and an I2 bump together. They have to come together, they smack together, and they react to form HI. Well, if you have less and less and less of the hydrogen, there's fewer of these to bump into the iodines. And even though we're not showing it here, the iodine is also decreasing. So you have fewer and fewer reactants available to bump into each other, so they don't bump into each other as often, which means the reaction slows down. The reason that these reactions slow with time is really a very practical reason. It's just there's not as much stuff reacting. And so because there's not as much stuff reacting, the reaction slows down. And in fact, for most reactions that aren't super fast, for the average reaction, they never really get to completion. Again, up to this point, we've kind of always pretended that everything gets to completion. Many reactions, unless you are playing doing some manipulation with the reaction to really force it to go to completion, most reactions, when it gets down to where there's just a very small amount of reactants left, it can stay in that state for a long time, because it can take a long time for those very few reactant molecules to find each other. So most reactions can get fairly close to being done without taking up too much time, but then when you have just a little tiny bit of reactant molecules left, it can take a long time for those to find each other. So all chemical reactions like this are going to slow with time, simply because there's not as much stuff to react. Okay, so I think this is pretty much what I was just saying. So the rate of the reaction generally slows because the concentration of the reactants decreases. Said that. At some time, the reaction stops either because the reactants run out or because the system has reached equilibrium. And we will talk about equilibria in the next chapter. And that is usually the fate of chemical reactions. The vast majority of chemical reactions, they don't actually reach completion because one thing we haven't discussed too much at this point, but you can also have reverse reactions where products are going back to being reactants. And so usually you do reach that equilibrium point. All right. I think we'll go ahead and call it there for this video. And in the next one, we'll pick up talking about the reaction rate again and defining what the reaction rate would be just for a generic reaction here and how we could write it for any given reaction that we might come across. So I'll meet you there in the next video.